Hi there and welcome to this video for Senior Physics on Electromagnetism and Electricity. In this video we're going to continue our explanation of electromagnetic induction and look at Lenz's law. Now basically Lenz's law is described after the scientist Heinrich Lenz, as you can see on the right hand side. Now this linked in with Faraday's law. Now if you remember what Faraday's law stated, he basically stated that an EMF induced in a loop was proportional to the rate of change of the magnetic flux through the loop with time. Okay, so we had this idea that we had change in flux over time. Now what Lenz did was basically put forward a proposal which was accepted, and he basically stated that the current induced in the conductor by a changing magnetic field is in such a direction that it's going to oppose the induced magnetic field that's been created. So it's going to go in the opposite direction to the rate of change. Okay, so let's explore this in a little bit more detail and try and explain why this occurs. Now, what you can see in the diagram here is we've got two solenoids and we've got a magnet at the top. Now you can see that the magnet produces a northern field line which is coming out of the magnet, and basically what's happening in the first diagram, we are pushing the magnet into the solenoid. Now according to Lenz's law, what's going to happen is it's going to oppose, the current is going to oppose the motion. So basically what we've got to have is that the magnetic field which is generated by the current in the solenoid has to go in the opposite direction to the field lines which are generated by the magnet. Now what is the reasoning behind this? Now basically we all understand from the first bullet point here that if we push a magnet into a solenoid, we've got electrons basically moving across that field. Now because electrons are charged, it then means that we've got a charged particle which is moving. Charged particle which moves generates a magnetic field. This is our secondary magnetic field which can interact with the magnetic field of the magnet. As a result, an EMF, an electromotive force, is generated. This produces a force on the electrons which produces them to move around the solenoid, which we call a current. Now basically what Lenz wanted to say was, if we pushed the magnet into that solenoid, it will produce a force on the electrons. Now if that force on the electrons pushed the electrons in such a way that they moved in the same direction as the magnetic field, what would happen is the two magnetic fields would combine. Now if the two magnetic fields combine, they will produce a stronger force. Now producing a stronger force on the electrons will push them faster and harder. That means that we're going to get an increase in current. Increase in current, increase in movement means an increase in magnetic field. So what we get is this knock-on effect that by pushing one magnet in, we're going to get a continuous increase in magnetic field which will just increase and increase and increase the amount of current which is generated. Now clearly this doesn't happen. So just to recap, Lenz stated that it must be in the opposite direction. So we are not creating more and more energy. Now as a result, he stated that it opposes the change in flux. So it's got to go in the opposite direction. So when you are looking at your solenoid, you must always make sure that the field lines that are produced in that solenoid are going to go in the opposite direction to the flow of current, to the flow of the magnet's field. So as you can see in the first diagram in the top left hand corner, as we push the magnet into the solenoid, we've got north and north opposing each other. Likewise, when we pull the magnet out, we're going in that opposite direction. And you can see that we then get our induced current changing direction as we move, pushing the magnet in, and then as we pull it out. Okay, so basically why Lenz stated this was to obey the law of conservation of energy, which basically stated that the energy going into the situation is going to equal the energy coming out. So that energy of pushing, doing the work, pushing that magnet into the solenoid, pushes the current round, but it cannot create any further electricity. Okay, so from that, what he then did, he added to them Faraday's law. Now you can see Faraday's law is written there, EMF, electromotive force, equals the change in flux, or delta psi, divided by the change in time, or delta t. What Lenz did was put a vector notation of a negative to show that it's going in the opposite direction to the change in flux. So when you look at the formula, you'll see the formula always written as negative delta psi over delta t, but the negative is Lenz's law and the actual formula is Faraday's law. Okay, now we can also add to this, obviously, by putting an n in the front, which is going to allow us to work out the electromagnetic force which is generated when we've got more coils which are generated in the solenoid. Okay, so to recap, Lenz basically stated that the current that is induced into a solenoid must produce a magnetic field which opposes the magnetic field generated by the stationary magnet. And it doesn't matter whether we're moving a magnet into a coil or a coil into the magnet, it's the same side of the same coin. But what you've got to understand is it's always going to be opposing the flow. That way we obey the law of conservation of energy. And how he showed this in his algorithm was the production of turning Faraday's law into a vector, where the negative shows it's going in the opposite direction. Okay, so let's look at a scenario as to how we can use this. So here I've got an example, and we're going to be employing both Faraday's law as well as Lenz's law. So we've got an apparatus on the other side, on the right hand side there. We've got a rod, A to B, which is in a magnetic field. So it shows that the metal rod A and B is resting on conducting rails connected to a galvanometer C and D. Now remember, a galvanometer is just a meter which can read the flow of current. So the apparatus, as we can see, is sitting in a magnetic field as shown. So what's going to happen is, we're initially going to be asked in A, will there be an induced electromotive force across AB if the magnetic field changes from a value of 2 times 10 to the negative 2 Webers per square meter to 0 in a time of 5 milliseconds. Then we're going to calculate the value of the EMF and the direction of the induced current around the loop A, B, C and D. Then we're going to see if the rod is moved to the right at the velocity of 5 times 10 to the negative 2 meters per second, with the magnetic field remaining constant at its initial value. We're going to be asked, will there be an induced EMF across AB? And then finally we will calculate the value of the EMF and the direction of the induced current around A, B, C, D for this case in C. So let's look at A. So will there be an induced electromotive force across AB if the magnetic field changes from the value of 2 to 0 in the time of 5 milliseconds? Well, the answer to this obviously is yes, because what have we got? Well, we've got a change in magnetic flux. And Faraday stated, yes, we've got a change in magnetic flux. Because we've got a change in magnetic flux, that's delta psi over delta t. So yes, there will be an induced EMF across AB as the magnetic field strength B is changing with time. Secondly, we're asked to calculate the value of the EMF and the direction of the induced current. Well, to calculate the value of the EMF, we're going to use delta psi over delta t. So we know that we've got 2 times 10 to the negative 2 times the area in which we happen to be in, because remember that is flux. So we've got to work out the flux using B and A. So we know the field strength is 2 times 10 to the negative 2, and we know the area around is 0.2 times 0.2. We know the time that it took is 5 times 10 to the negative 3 seconds. Remember, it's in milliseconds. So we calculate all that through, and the EMF comes out as 0.16 volts. Now, as with direction, Lenz's law will require the decreasing magnetic field to be opposed. So it's going to go in the opposite direction to that change in flux. So the induced current around the loop will produce its own field to reinforce the original field lines. This requires a clockwise flow of conventional current around A, B, C and D. Okay, so remember we've got to go in the opposite direction to where that change of flux is working. So part C asks, if the rod now is moved to the right at a velocity of 5 times 10 to the negative 2 meters per second, the magnetic field will remain constant as what it started at, which is 2 times 10 to the negative 2, and we are then asked, will there be an induced electromotive force across AB now? So obviously yes, there will be an induced EMF because this time the area is changing between the magnetic field remaining constant. So you've got, even though you've decreased or kept a constant magnetic field, you're decreasing the area. And remember, magnetic flux is B times A. So if you change A and you keep B constant, you still got a change in flux. So as a result, you must still get an induced voltage there. And the question then is asked, let's just double check, calculate the value of the EMF in the direction of the induced current A, B, C, D. So we know that EMF equals the constant magnetic field strength times the change in area over delta T. As area is changing because side D and A is increasing at the rod's velocity, so as a result what we've got is that the magnetic field is changing based on the speed, and we know that DC remains constant, but we know that speed is going to change, so we get 2 times 10 to the negative 2 times 0.2 times 5 times 10 to the negative 2, remember that's the speed, and 2 times 10 to the negative 4 is the EMF, which is calculated. Okay, so that basically hopefully explains Lenz's law to you, gives you an area to work through with respect to an example. So I hope you found that useful. I look forward to you joining me again. Thanks for watching.